Okay. Hello, I'm David. This is a revision seminar for engineering differential equations for engineers. It's semester 1, 2021, and this is the second seminar where I'm giving this semester. I'm doing it from home, so I can see my bookcases. And I've been asked to talk about transform methods in differential equations, especially for ODEs. Okay. So the big idea of transform methods has a lot of pieces, and I just want to talk a little bit about how I understand them in case it helps. If it doesn't, then please feel free to ignore some of the things I say, or just pull out the bits that make sense to you. Right, so let me just talk this through. In physics mainly, but in linear algebra as well, there's this thing where you could set up calculations about some object in space, or some object in space, and if it was I'll do it in the plane first. If you had an object like this in the plane, you could set up equations involving it to figure out slopes and stuff like that involving this, and you could use the x and y coordinates to do it, but it might be easier to set it up with the oh, my video's frozen. Oh, that's okay. Set it up with the coordinates here, because then if I turned it, it would be nice and symmetrical around these axes, and all my calculations would be a little easier. That's something that we do with coordinate systems. And the function thing is similar. And the idea is that calculations I would do here might be difficult, but calculations I do here will be easier. And then once I've figured out what's going on, I can always transfer it back and rotate it to get the answer that I wanted. That's the general concept. And it's also related to the idea of a basis in linear algebra with vectors and matrices. So that this here is saying, well, I could write this point as a combination of a vector on this and a vector on this, but I could also write it as a combination of a vector on this and a vector on this. And so that idea of rewriting things in terms of a new basis is what this is all based on. Okay, so with functions, functions have this cool property. Well, it's not really that cool, but if you take a function and you take another function, then if you do this, then it's still a function. And that's how vectors behave as well. You take two vectors, you add, multiply by stuff and add them, you still get a new vector. So what mathematicians have done is they've taken some ideas from the way vectors work and applied them to the way functions work. Okay, and then there are things called linear transformations, which have the property that if you do the transform first, so if you do the thing and then add or multiply by scalars, then it's the same as add or multiply by scalar and then do the transformation. And differentiation is one of these. So if I do differentiation first and then add functions together and multiply them by stuff, it's the same as multiplying by, adding and multiplying by stuff and then doing the derivative. And I'll get the same answer either way. And you've been doing this from the beginning of doing differentiation. Because whenever you saw something that had all these pluses between, you just did all the derivatives separately, and that was okay. So the thing is that there's lots of things you can do to functions that have this property. If I have two functions and I want to, my operation is transformation, I'm supposed to call it. And the thing I'm going to do is multiply by x. Then if I add them together and then multiply by x, it's the same answer as if I multiplied by x separately and then added them together, because that's expanding that thing. And cool, and differentiation does it as well. So that's one thing I could do. Do d on dx. If I do d on dx, if I add them together first and then do the derivative, it's the same answer as if I did the derivative and then added them together. So what these transform methods are doing, no, not there yet. So now we're up to what I really wanted to say. If I wrote something like this, like that, this action of doing this to a function y, of multiplying it by minus 36 and also finding the derivative and multiplying that by x and also finding the second derivative and multiplying that by x squared, that entire thing that you do is linear. Meaning if I have two functions and I add them first and then I do this thing, I'll get the same answer as if I did this thing separately to the functions and then added them together. That's really interesting. And if I want to figure out which functions make this come out to 0, then I should be able to just find some functions that make it come out to 0 and add them together. That's great. But this is a really complicated thing. It's got derivatives, it's got multiplying by stuff. If I could figure out a different way to write my functions, like a different thing to shift everything around or upside down or backwards or something, maybe there would be a different way to do this action. And that's the idea of the transform methods. All right. So transform methods go, for example, the Laplace transform. So the Laplace transform will take a function which is a function of time, and it will reproduce a new function which is traditionally called capital F, and it will be a function of S, which is apparently frequency. And this is linear as well. If I add functions first and then do the Laplace transform, it's the same answer as doing the Laplace transform separately and then adding them. And the big idea of a Laplace transform is that doing the derivative here is the same as multiplying by S here. And taking off the original value. This calculation is easier to deal with than this calculation. And that's why people use Laplace transforms. I'll talk about what they are in a second. And Fourier transforms take a function which is a function of x, I believe. Just give me a second. You're allowed to use whatever letter you want. And what it produces is a new function called f hat, which is a function of w. And importantly, derivatives here go with this. I'm going to have to look this one up. I've only just learned Fourier transforms this year, so multiplying by I times W. So unfortunately, the Fourier ones use complex numbers, but we can be all okay with that. So that's the two things. Jacqueline, you've asked a very important question. When is it better to use one over the other? Not 100% sure yet, but I'm pretty sure that these only apply to certain kinds of functions. So I'll have to get back to you on that. Okay, but that's how they're similar in terms of the idea is that they do things to derivatives, which is what makes them useful for differential equations, and how they're different is the way that they do the transformation, obviously, but they're also different in how they behave with differentiation. You notice they're quite similar though, because differentiating here is the same as multiplying by s here, but I've got a little adjusty thing to do. Differentiating here is the same as multiplying by w here, which is the variable, only I've got to adjust by I. Okay. So, yeah, I'm not 100% sure why it would be better to use one over the other. Yeah, and I don't actually know that, and I can't see it in the notes yet. So that's a really good question to ask your lecturer if you want to know that. I wish I could answer it. I'm sorry. Okay. So they're the big ideas, and it would be useful for each of them to have an idea of what functions here produce what functions here. How are we feeling at the moment about this vague general beginning bit? All right. Okay, just give me a moment to process my thoughts, and I'll be back with you in just a moment with more stuff. Okay. All right, let me talk about Laplace because I'm more familiar with that, and I was specifically asked to talk about it. But I promise I will talk about Fourier. So if I get to an hour from now and I haven't,
I don't get paid. I won't do it.
What's that? I was a bit confused by that. So if I feel free to stop me in about 45 minutes if I haven't talked about the Fourier. Okay. Okay. So, cool. This is the big idea of Laplace transforms, but there are some other ideas as well. And Laplace transforms, they went into quite a lot of detail in this course. And we're going to specifically deal with them with PDEs. And I'll try and find an example to do them with. But first, there's a definition which has got an integral in it, which I would have to look up. Just a second. Which I'm not going to worry too deeply about today. I'm just going to write it down so that it is written down. The Laplace transform of, whoa. If there's anyone here who's trying to be in 2 Zooms at once, which I'm getting, yeah, could you please make sure that you know which one you're in the chat for? I'm just trying to find the definition. The Laplace transform of a function t is called traditionally capital F, and it is the integral from 0 to infinity of e to the minus st f of t dt. Okay. One thing I notice about this is it begins at 0. And I think that means that when you're doing the Laplace transforms, it's specifically designed for functions that start at 0. And so it doesn't matter what happens to them before t is 0, it only matters what happens after t is 0. So it's for functions that start with t being greater than or equal to 0. Okay. So if your function is, that's one thing about it. And then there's rules for the kinds of functions they deal with. This will be able to deal with with functions that start at 0 and go forever. So I think in answer to the question about which kind is better, pretty sure the Fourier ones are of a different kind. Okay. And actually, if I'm going to look this up, I want to compare them. Fourier transforms are designed for functions that go from minus infinity to plus infinity. So that's a difference that's worth pointing out. All right. So I was saying to someone yesterday, when you multiply 2 functions together and you do the integral of them, that's like doing the dot product of 2 vectors together. And so what the Laplace transform does is it tells you what the dot product is between your function and e to the minus thing. And e to the minus st is a function that goes downwards like this. And the s will be going down at different speeds. Higher s's will go down faster. Okay. And I'm pretty sure the s's end up being greater than or equal to 0 as well. Yes. So higher s's go down faster. And so the dot product for vectors is designed to tell you how much of one vector is pointing in the same direction as another. That's what the dot products do. If they're pointing in the same direction, the dot product will be large. And if they're pointing in perpendicular directions, the dot product will be 0. And so what this is telling me, directions for vectors, for functions, is just lining up well. And so this is trying to guess how quickly does the function f decay? Really? And does it decay at the same speed as this, or a different speed to this? Or possibly it decays at 2 different speeds simultaneously. Pardon me. And so that's what it's trying to do. For every possible speed of decay, it's trying to line it up with a function that decays at that speed to see how my function decays. That's my general idea of what it's trying to achieve. Yeah. But I could be making that up. People talk about it as time and frequency, and I think the exponential goes with a sine and the cos. Yeah. Anyway, I feel like it's a decaying thing. Right. That's what they are. And it turns out that if you do those calculations, there's a big table that tells you what things become. And so over here, if you've got a function which is, we can just look them up. I don't have one with me, but they're easy to find online. And there should be one inside your course, a table of Laplace transforms. Yeah, any number of them floating around the internet. I actually quite like the one in your course. I find it a little easier to read than most of the ones that you see. A lot of these are literal photos of things from textbooks. Yeah, that's hilarious. So I'm going to write some of these down on my piece of paper. 1 as a function of t becomes 1 over s, which is the beginning. And sine and cos are really important too. I believe in yours it has a w in that spot. Right. These are the sort of most important ones. And then we have the rule for what happens if you differentiate and integrate things. Even this is already one of these. Cos is the derivative of sine, which means that what you should be doing is multiplying by s, basically. And we had to divide by w because it's actually the derivative would have a w in it as well. Yeah. Okay. Awesome. So I don't remember all of them, and I need a table to look them up. If someone could send me the table from the course, that'd be awesome. Feel free to volunteer. Thanks, Fraser. Then I can look up the ones that are important to this course. But the important rule is how derivatives behave. Thank you. You can stop sending now. I'm very nice. Awesome, that's so much better. This is the one from your course. It's got a whole lot of things. It's got polynomials. It's got e to the power ofs. It's got sines and coses. And it's got u's and deltas. Okay. So I just want to point out something, that u of just t, this u function here, u of just t is 1 when t is positive and 0 when t is negative, which means that if I'm only interested in functions that start at 0, it's technically the same as just 1. Yeah. But if this started a little different spot, this would be when t is greater than a, and 0 when t is less than a. And so this function, 0 here, 1 here, this function is 0 here, 1 here, and it switches over at the point A. So this function is important. This function is really important if I'm considering things for t greater than 0, because it has its change after 0. This function, if I'm only considering functions with t greater than 0, it's the same as the function just 1. And you'll notice in the Laplace transform table that e to the minus 0s over s is, e to the 0 is 1. It's the same as 1 over s. So when t is 0, 1 over s becomes u of t. But just a second, 1 over s just becomes the function 1. They're the same thing when you're talking about Laplace transforms, because I'm only thinking about what happens when t is greater than 0. So I don't know if this was the most appropriate thing to say it, but that's something I realized this semester. Okay, that's just an idea of what that function does. Okay, it's this second page which allows you to create what the Laplace transform is for a whole lot of other functions. And so there are a few useful bits of information that can allow you to create one Laplace transform from another. So the most important one is how derivatives behave, which is this one just here. But what that looks like on paper is the thing I drew already. If you know that this function becomes this function via the Laplace transform, then doing the derivative over on this side is the same as multiplying by s and minus f of 0. And that's really useful for dealing with differential equations, and I will get back to that. So that's one of the theorems. And if you do the second derivative, then I'll multiply this by s and take off f dashed of 0. And the third derivative similarly. The other thing is what happens when you replace t with t minus a, because that's something that happens a lot with the u's and whatever. And what happens over this side if you replace s with s minus a? And they're called the shifting theorems. So if you know what f of t becomes, or what little f of it, or what capital F of s becomes, either way, the inverse Laplace transform goes this way. Then I want to know what happens when I do various things. So multiplying over multiplying this over here by e to the minus as is the same as over here multiplying by replacing, multiplying by, no, ignore that. So it's replacing t with t minus a, and also multiplied by u of t minus a. And so I end up with f of t minus a, u of t minus a. This is the one of the shifting theorems, the t shifting theorem, because what I've done is I've replaced the t with t minus a, which shifts the function forwards. On the other hand, over this side, if I times this by e to the at, I get e to the at f of t. That's the same as over this side, replacing s with s minus a. Yeah. So those are the shifting theorems. Which means that I can now think about what happens both when I shift things and when I multiply things by e to the whatever. These here are the important theorems for, this is for figuring out what the Laplace transform is, and this is for figuring out what to do with derivatives. And I'm going to actually do an example now. But first, let me do one example of using this. So I know that the function 1 becomes 1 over s. And so if I multiply this by e to the 3t, then that's the same as replacing s with s minus 3. And so this will be 1 over s minus 3. That's how that theorem works. Yep. And so it requires us to be able to recognize these things and be able to deal with them. So now I'm going to do an example of using Laplace transforms on a PDE. I think I actually already have a video on using them for ordinary differential equations, but let's do them on a PDE and see if we can deal with this. How are people feeling before I do this example? Okay. I'm just looking for an example. Okay. Oh, yes, I love dumb questions. I was just making it up in this example just here. It's just an example. If I happened to just put a 3 there, I was just imagining what would happen if it was a 3. But if it was an 8, it would just as easily become an 8 there. I was just, instead of using the letter A, I was using a number, that's all. Okay. So I've found an example I'm just writing it down. So I have this differential equation. It's a partial differential equation because it involves partial derivatives. And it looks like we have that the function w is a function of both x and t. So this feels like it's describing something on some physical object which is stick-shaped. But it goes on forever, possibly. All right. And so this is to, I don't know what this is. Could be a beam of light. It could be a string. I don't know. It didn't say in the problem what it was. But this is the story that's going on. And then at various different times, this W will be various different values at different places. So presumably it like oscillates up and down or something. That's my guess. Okay. And this is telling me what W is, that at time 0, no matter what x is, the value of W is 0. So if I imagine W as a function up and down, then it's just completely flat at time 0. But, and also at position 0, when time, for all time, it's always 1 here. So I'm guessing maybe this is a heat thing, that it's being constantly heated to the same temperature here, and that temperature is called 1, and then that is pushing forwards through the thing, maybe. That's just my guess. I don't really know. I'm just trying to come up with a thing that makes sense to me. Okay, so the value of W is always 1 here, no matter what time it is. It doesn't make any sense. I don't understand. This mustn't apply when x is 0, right? Because otherwise the answer would be 1. So there's something weird going on there. It's going to run with it and see what happens. Okay. This has 2 variables, and the traditional Laplace transform is only a function of 1 variable. So what I'm going to have to do is I'm going to have to imagine that w x of t, if I imagine that the x is a specific spot, and I think about what happens as time moves, then I can think of that as a function of just t if I think of the x as a constant. Right. So that's the idea I'm going to be using. So I'm going to say that capital W of x and s will be the Laplace transform of little w of x and t. So I'm pretending the x is a constant, and I'm thinking that capital W of s is the Laplace transform of little w of t. But x is a variable. It will be a different constant at different times, not different times, different constant at different places. And so I still need the x in there to tell me which function w I'm thinking about. Okay. So that's what I'm going to do. And so up here, this is dw on dx. Here we go. So dw on dx is also a function of x and t. Damn it. Run out of... So dw on dx is also a function of t if x is constant. And doing the action of differentiating with respect to x won't make much of an effect on how the Laplace transform works, because they're both linear functions of functions. And so this is going to produce, when I do the Laplace transform of it, d on dx of capital W xs will be the Laplace transform of dw on dx. I should have written it the other way around, I'm sorry. So what I'm thinking here is I've started here by looking at Laplace transform. I'm going to Laplace transform each piece of this. All right, here we go. So the Laplace transform of just W, of little w, is capital W. And the Laplace transform of dw on dx is d capital W on dx. All right, and here the Laplace transform of dw on dt, well, that's the derivative of little w with respect to t. And I know what Laplace transforms do to derivatives. Doing the derivative of the function is the same as multiplying your original function by s and subtracting the value of the old function when t was 0. But little w also has an x in it, so I'm going to have to write that in. And according to the original information I was told, little w of x0 is 0. How are people feeling about what just happened? So why don't I do that for the dw on dx is a very important question. It's because the x isn't the variable that the Laplace transform is acting upon. Yep. So I feel like I need to just step back and deal with an ordinary differential equations for a minute and come back to this in a second. Okay. It was an ambitious plan. Let me do an ordinary differential equation and see what I can do. Maybe not, just a second. Little w, so the rule that we've got here that we're working on is, I'm just going to put it here, that the t becomes an s. A function of t becomes a function of s. That's how Laplace transforms work. But it doesn't make any difference to what the x is doing. Because the integral that you do to do the Laplace transform is an integral dt. And so the x will count as a constant with respect to that integral. And so if the f of little t becomes a capital F of s, then doing anything to this involving x isn't going to make any difference to the Laplace transform. So the Laplace transform of d on dx of some function is going to be the same as d on dx of the Laplace transform of that function, because the x doesn't get changed by the Laplace transform, only the t's do. And so when I write this, d little w on dx, when I do the Laplace transform, the little w becomes a big W, but the d on dx stays the same. How are we feeling about that? Cool. Took me ages to sort that one out. Okay. So the parts of my equation I've dealt with are, I've dealt with this. But I do know that multiplying by a constant doesn't make a difference to the Laplace transform, in the sense of that you multiply the constant first, you get the same answer as if you multiply the constant after. So if I'm just going to be really explicit about this, the Laplace transform of x times dw on dt will be the same as x times whatever the Laplace transform was before. So multiplying it by a constant will still be there after you do the Laplace transform. And the constant in this case is x. It's not constant when I'm thinking about dw on dx, but it is constant when I'm thinking about the Laplace transform, because the Laplace transform only affects the t's. So this is constant when thinking about t, and when I'm doing the Laplace transform, I am thinking about t. Okay. How do you feel about that? Awesome. Right. Doing well. We have dealt with this bit. We have dealt with all of that bit now. Now we have to deal with this bit. The x is just a constant all by itself, like with respect to the Laplace transform. So I really need to know what the Laplace transform of 1 is. The Laplace transform of 1 is 1 over s. And the Laplace transform of x times 1 will be x times 1 over s. Now I have dealt with every piece of this formula. All right. So just to be absolutely certain that I'm doing this correctly, I'm going to write the original formula and replace each piece with the thing I figured out what it was. The d little w on dx became a d big W on dx. Oh, that wasn't an s, that was an x, wasn't it? Sorry, in the original formula. Getting myself all confused. X d little w on dt became xs capital W. And the x became an x on s. Okay. So here we are. Now we have turned all the t's and the d on dt's into s's. So that was the first stage of our working. First stage of our working was to do a Laplace transform, turning the little t's into s's, and I've done that, and the Laplace transform will also turn the d on dt's into s's as well. All right, but the x's stayed where they were when I did this process, because the x's weren't involved in that Laplace transform, it only affected the t's. So the d on dx's stayed where they were, and the x's stayed where they were. Okay. If you do a lot of practice with Laplace transforms, I'm sure you would be able to do this more quickly. All right. And now, this is a new differential equation that's only got one derivative in it, a d on dx. So now I'm going to just briefly imagine that the s counts as a constant now. I'm going to switch my perspective. I'm saying, well, there's no d on ds's here. It's an ordinary differential equation now. And these s's count as constants. This is a linear differential equation. I could do it with integrating factors, I imagine. And so if this came from the product rule, then this this is the derivative of that. I need this to be the derivative of whatever's in this spot here. So I'm just going to check what the answer is. Yeah. So I need to multiply by something in order to arrange that. And so the thing I multiply by is e to the integral of that. The s will still be there because it counts as a constant in this story. The x will go up to a new power, and I'll divide by that power. Okay, and so the integrating factor will be e to the that, not half, sorry. Went up to 2 and I divide by the new power. Got myself a bit confused there. And so then if I multiply everything by this, like that, then it will automatically be set up so that this is the derivative of integrating factor times w. And then this would have to be differentiated. So at the moment, the thing I'm doing has nothing to do with partial differential equations or Laplace transforms really at all. I'm going all the way back to the very beginning of the course and in technically all the way back to Maths 1B and doing the strategy for solving differential equations that look like d thing on dx, thing times function of x times thing equals function of x. Where'd my sharpener go? And so I'm going to have to integrate this. I can cheat a little bit because I know that this is the derivative of this. That's how it was set up. We set this all up specially so that that would happen. And so I can see an x, I can see an x times e to the half of sx squared here. And I can see an x times e to the half of sx squared here. So if I arrange this just a little bit differently and pull the one on s out, and then do this, this would be the same as just a second. Times by s on the top, that'll give us the sx, and so it'll be 1 on s squared. There's a little trick to go, if I times s here and times s here, I'll have xs on s squared, and I'll pull the s squared out, leaving me with sx so that this matches with that. Oh, could I have done this as characteristic? Okay, so I've just had a question. How do I know when to use characteristic versus integrating factor? If this had been a 0, then I could have used the characteristic one. I could also have used the characteristic and attempted to find a particular solution that would have worked as well. So I could have done either. So integrating factor is specially designed for one where there's a function in this spot. Oh, crap. No, it could have worked. Either could have worked. Didn't even think of that. No, characteristic is designed when this is constant here. No, I've got it. So if it had just been S with no X there, then I could have used characteristic equation and particular solution. But because there's a function in this spot, I have to use integrating factor. That's the difference. Does that actually answer the question? So I'm going to just say that the fact that this is a function of x that involves x's that was my thinking. X is next to w caused me to think of integrating factor. I'm going to move forward. So I've got e to the half of sx squared w equals 1 over s squared times this integral. And this integral was e to the half of s x squared plus a constant. But remember that constant could be a function of s because when I do this derivative backwards, these d's really are curly d's actually. I've written them as straight d so that I can figure it out, but right back at the beginning, it's a curly d. So any constant that I create will have to be a function of s. Oh man, they said a homogeneous in a particular. Oh, maybe I've done something wrong there. I'm sorry, I don't really understand that in the solution. I can divide by this. Dividing by e to the power of it is the same as multiplying by e to the negative power. Yeah, I always thought that homogeneous and particular ones only went with linear ones with constant coefficients, but I could be wrong. Okay, so now we have an answer for what W is. Okay, this is capital W. Yep. All right. This is capital W, and it needs to be okay, just a second. What just happened? We started out with an equation. We went through all this effort of doing the Laplace transform, and it turned it into an equation that involved s's, but all the derivatives with respect to x are gone because Laplace transforms turn derivatives with respect to s back to t. Sorry, derivatives with respect to t are gone now because they became multiplying by s. And so I'm left with derivatives with respect to x. And the way that I'm going to deal with those is I'm going to solve this equation the way I used to solve equations that only had one derivative in them. And I got to here. Now I'm going to have to undo that Laplace transform to get myself back to where I came from. And so I'm going to need to do the inverse Laplace transform of big W to figure out what little w is, because that was the goal here, to figure out the function. I may have a chance of figuring out what the constant is at this time. Okay, so I'm just going to deal with that. I might be able to figure out this constant now, because something I didn't do right at the beginning is I didn't transform everything. Because when I did that Laplace transform, I used this when I did the derivative. So when I did this derivative here, I used that condition here, but I didn't use this yet. And so maybe what I should do is Laplace transform this as well. So I should go back to when I was doing Laplace transforms and deal with that. Okay. So when I Laplace transform this, I will create capital W. The x is still there, and the t will become an s. And when I Laplace transform 1, I'll get 1 over s. So when I did that Laplace transform right at the beginning, I could have done this calculation and gotten to here, this with this information creates this with this information. Damn it, that wasn't an S, that was a 1. Like that. The initial values for t, let me check what I've done here. So I want to make sure I've covered everything. The original thing had an initial condition when t was 0, and I used that when I did the Laplace transform of the derivative here. And then the boundary condition, because it has a t in it, and it will still have a variable involving t, I can transform that. Because it's a function of t, I can do the Laplace transform of that. So it seems that things where there's an initial value involving t will not specifically be Laplace transformed. They'll only be used as part of the Laplace transform of the derivative. That's what seems to be happening here. So we are at this point. So capital W when x is 0 and s will be that, which comes out to this, because e to the 0 is 1. And this answer is supposed to be 1 over s according to the Laplace transformed condition. Okay. I'm going to run. I don't really know what to do with that at the moment, but I'm going to maybe put it over a common denominator. So now I know what the C is. I can put that back up here and get that W, capital W, is now 1 over s squared plus s minus 1 over s squared e to the minus half of sx squared. Okay. So now I have what capital W actually is. And I can remind myself that capital W is a function of both x and t and s. And so if I do the inverse Laplace transform of it, it should produce something involving little w and x and t, which was the goal. So I need to know what the inverse Laplace transform of all these things is. Okay. Well, straight up inverse Laplace transform of 1 over s squared, I can look that up in the table. I know what the inverse Laplace transform of 1 over s is. And dividing by s would be the same as differentiating. So I have a feeling this is going to go to t, but I'm just going to look it up. Yep. Okay. The multiplying by e to the, now here we go. When I do this Laplace transform, the x is counting as a constant now. So in this one, this is e to the something times s. So I have a rule for that. When I multiply by e to the minus as, it's the same as over this side, replacing t with t minus a, and multiplying by u of t minus a. So that's what's going to happen when I multiply by this. As long as I know what the inverse transform of s minus 1 over s squared is. Oh, I shouldn't have should have left it like this because I know what those are. Honestly, don't care. Okay. So I know what this one becomes. That'll become 1 minus t, because that's what they become. And multiplying by e to the minus stuff times s is the same as replacing t with t minus this thing, and multiplying by u of t minus this thing. Okay, that's because this is that. I should have written that first. So little w of xt is now t plus 1 minus t plus a half of t of x squared times u of t minus a half of x squared. Yep, and that's the answer. If you felt like it, you could possibly have expanded this out back here instead of what I did, and maybe an alternative way of representing it might have been this times the u minus this times the u. Maybe that feels better. Okay. So what just happened? I had my original equation. I noticed it was a function of both x and t. And I noticed that if I held x constant, and this would count as a function of t, so I could do a Laplace transform in it to turn the t's into s's. And importantly, it would turn the d on dt's into s's as well. So I figured out what every piece of this became. This piece here, the little w becomes a big W, derivative with respect to x that doesn't change when you do the Laplace transform. Derivative with respect to t becomes multiplying by s. Timesing by x is the same as timesing by x. 1 becomes 1 over s, and x therefore becomes x over s. So that's what I did. I turned each piece of this. Oh, and there was one more piece, which was this thing, which is also a function of t, so I can Laplace transform that too. So all of that got changed into this. Managed to replace each piece with something involving capital W and S instead. And now I notice this is an ordinary ODE, so I attacked it with what I thought was the best plan, which was an integrating factor, but maybe there was a better plan. And that eventually, but there was a little technical detail when I did that when I did the plus C, it had to have an S in it because it wasn't really a straight D, it was a curly D. And then I had to un-Laplace transform this. Inverse Laplace transform it. And so what I did is I used the table for the 1 over s squareds and the 1 over s's, and I used the shifting theorem to deal with the e to the whatever. And that got me to a final answer. Pardon me. Where are we up to? What do you want to, how do you feel? Shifting theorem? Oh, yeah, that is the inverse Laplace transform there. So I'm just going to go through that bit that just happened here. This is the bit you're talking about, Declan. And yes, we will definitely look at the Fourier transform, and I will go over time if I need to, because I don't have anything after this. Okay. So I know that the shifting theorem says that if I have something and I know if I have something involving s and I know what its t version is, then multiplying by something, an exponential, will be the same as shifting this. So I know that 1 over s squared, because I looked at the table, the 1 over s comes from 1 in the table, and the 1 over s squared comes from t, like that. But what I've done is I've multiplied by e to the minus half of x squared lots of s. And the shifting theorem says that multiplying by e to the minus something s over this side is the same as replacing t with t minus the thing, which was a half of x squared, and also timesing by u of t minus the thing. And so this will be 1 minus t minus the thing, because I replaced the t with t minus thing, also times by u of t minus the thing. And that's how I did that move. Let's move here. I only just thought of this arrangement of it this year, and I just feel so much better about it than I used to. Okay. Let's do the Fourier. I'm sure we could talk about Laplace all day long and the algebra of doing it when you have to do partial fractions, but I really want to talk about Fourier. Right. Before I move on, that move of imagining this as number times s is really the key to making this process work. So that was all Laplace transforms. And Laplace transforms are designed to compare your function to e to the minus something, to decaying things. And what it does is it turns differentiation into multiplying by s. And Fourier transforms are designed for comparing your function to oscillating functions as opposed to decaying functions. So the Fourier transform of f of x is defined to be, just looking it up, one over 2 pi times the integral from minus infinity to infinity of f of x e to the minus I wx dx. If you look very closely, this dx, after I've done the integral, is going to be replaced with minus infinity and plus infinity, so there won't be any x's in it afterwards. And the name, so this thing is going to be a different answer for different w's. And so that means it's a function of w, and it's called, the traditional notation is f hat. So the idea is that if you have little f of x, it will become, under the Fourier transform, little f hat of w. And the inverse Fourier transform can also be done with an integral. And it looks extremely similar to this one, but it has a plus in this spot. And it's a dw, because by the time I've finished it, is it root 2 pi? It totally is, sorry. Thank you. By the time I've done this integral, all the w's will be replaced with numbers and I'll be left with x's. All right. That's the definition. And we compare it to our Laplace transforms. They both have your function times another function. And actually that function involves an e. This one involves an I, because putting the I in will automatically include both cos and sine. Because when you do e to the I something, you get a cos and a sine when you do that. So that's why this one is comparing to oscillating functions. We just put the I in there along the way. So just while I'm at it, there is actually 3 Fourier transforms mentioned in your notes. I just want to write them all down on the one page so that they're together. There is the straight f of x, which is 1 over root 2 pi minus infinity to infinity of f of x e to the minus I wx dx. And then they mention a Fourier cos transform, which is this, like that. And this is only designed for even functions. And they also define a Fourier sine transform, which is exactly the same, but with a sine in this spot. And this is designed for odd functions, as far as I can tell. This was something that took us a while to notice in the Maths Learning Centre when students were coming to talk about these things. So if it just says the Fourier transform, it means this one. If it says the Fourier sine transform or cos function transform, will be one of these two. Not 100% sure how these are related. I'm pretty sure that if your function is even, then the bit involving sine will disappear, because the integral of an odd function from minus somewhere to plus somewhere is 0. Yep, how to use Fourier transform to solve PDEs, that's what we're going to do. I just wanted to set it up so it was here, so that in future semesters we have this information here. Okay. All right. Give me a moment. All right, but before I do that, if we're going to use it to solve differential equations, we're going to need to know how it interacts with derivatives. It would be really useful to have a big table of Fourier transforms, but I don't think they provide that in your course. That would be too easy. Just give me a moment to see if I can find one. Oh, there is one. Awesome. Yay. Thank you so much, people. Oh, thank you. Life is so much better. So they're all the definitions. This is what the derivatives do. Yeah, well, that doesn't tell me what the answers are for any particular functions. That's the problem. I would like to know what the Fourier transform is of, say, 1. And that sort of thing. But it looks like we just have to calculate it ourselves. Okay. Worry not. We'll sort that out. Yeah, this is what makes me upset. Okay, that's all right. That's all right. We'll be okay. All right. So I think there's rules for what sorts of functions actually can do Fourier transforms. I think it says that it has to be piecewise continuous, the derivative has to be piecewise continuous, and it has to be the integral from minus infinity to infinity of the absolute value of the function squared has to actually exist. So in general, your function has to decrease as it goes out to infinity, otherwise that's not going to work. Yep. Okay, that's fine. Or it has to be 0 outside a certain zone. Ah, that's cool. So I have a question. In the notes, or in the Mobiuses, did it say what the Fourier transform was of U? Like, did you figure that out at some point?
Usually you just split up the domain from like negative infinity to 0, and you just consider f of x as 0 for that. And you do 0 to infinity, you consider f of x as 1 for that.
The integral. Is that what you're saying?
What's that?
You just have to actually do the integral to figure it out?
Yeah, but like you don't have to do half integral from 0 to infinity, because then you just consider f of x as 1 for the domain that the stepwise function is 1.
I just want to do this, if that's okay, just to make sure that I know what's going on here. So this function here, u of x minus a, at the point a, it's 0 before it and 1 after it. And u of x plus a, at the point minus a, it's 0 before that and 1 after that. So if I just split into all three zones, then u of x minus a minus u of x plus a is 0 minus 0 here. 0, no, wrong way around. So should I have done it this way? Yes, awesome. I just want to make sure I've got this all right because I don't. So u of x plus a would be 1 after I switch between 0 and minus a, because this is equal to 0 when x is minus a. And it's the input is negative when x is less than minus a and positive that side. So this will produce the answer 0 in this zone, the answer 1 in every zone after this. And this one will produce the answer 0 in every zone before a and 1 afterwards. So if I subtract them, I'll get 0 minus 0 here, 1 minus 0 here, and 1 minus 1 here. And so this function is 1 between minus a and 0 everywhere else. And so if I did the Fourier transform of it, then that'd be the integral from, well, 1 over root 2 pi, the integral from minus infinity to plus infinity. E to the, sorry, that'd be too easy. E to the minus I wx dx. But this function is 0 all the way out here. And so the integral doesn't really exist here. Like the integral will be 0 in this spot and it'll be 0 in this spot. And so I'm going to get just the integral from minus a to plus a. And the answer for this in that zone is 1. Like that. Is that the sort of thing you were talking about?
Yeah.
Cool. And so let's see. E to the power of anything will still be what it was before, but I'll have to divide by the constant derivative. And I can take that out. Because it doesn't involve an x.
Shouldn't there be a negative taken out as well with the IW?
Yes, there should. Good noticing. And that will be e to the minus IWA minus e to the minus IW minus a. Okay. Oh, I've got feelings here. So this minus I brought inside the brackets so that I can switch those two around. Ah, yes. So if this had been divided by 2, like that, then this would be shine of IWA, which is so cool. Ah, that's cool. What how shine interacts with I? Actually, even better. No, I don't want to do that. That was fun, but I decided I don't want to do it because the other thing I could do is that this would be cos of cos of WA minus sine of WA. Plus sine of I times sine of WA, and this would be cos of WA minus I times sine of WA. And so I'm going to get cos of WA minus cos of WA, and I sine of WA minus minus I sine of WA. So I'm going to get 2I sine of WA. Oh, and the i's cancel. Oh, it's so beautiful. Huh. Well, there you go. That's just remarkable. Yeah. So apparently shine of IWA is I times sine of IWA. Okay. And that's the answer. I think this is the same as root 2 on pi. So we do have one entry for our table of Fourier transforms. We know that u of x plus a minus u of x minus a, when we do the, damn me, that's a Laplace transform. When we do the Fourier transform, that becomes root 2 on pi sine of AW over W. We know that. Not sure if we're allowed to reuse that, but at least we know. Okay, so that was calculating that. Now we want to use it to do a PDE. I'm going to look something like that up. But before I do, how are people feeling about the moves that were made there? I will tell you one more thing for complex numbers purposes. One piece of information that is extremely helpful, which is when I divide thing by I, it's the same as multiplying the thing by minus I. Just for future reference, if you've ever got a divide by I that doesn't cancel out like mine did, this is a way of dealing with it. So dividing by I is the same as multiplying by minus I. Just a useful piece of information if you didn't know that. Okay, let me see if I can find an example of using this for something. Huh. Just give me a sec. I want to share something. These are some practice solutions. So here it says find the Fourier sine and Fourier cosine transforms of f of x equals x. Okay, so I was getting a bit confused because I said earlier that you can only do Fourier transforms of functions that Fourier cos transform if the function is even, and you can only do Fourier sine transforms if the function is odd. And this function is only defined for 0 and above, but I can create an odd function from that by doing an extension. Right. So I'm allowed to do the Fourier sine transform on a function that isn't even, that isn't odd, as long as it's only defined for positive numbers, and I define it to be minus whatever it is for the negative numbers. Okay. That just freaked me out a bit when I saw that on the page. All right, I'm going to try this one. Uh, 1D wave equation localized source. I'm not 100% sure what localized source means, but it tells me that this is what it is. Phi of tt is equal to c squared of phi of xx for x between minus infinity and infinity and t greater than 0. And then the initial conditions are that phi of x0 is a function, which they haven't told me what it is. Phi sub t of x0 is 0. Okay. All right. So I'm going to be seeing if I can figure out how to do this, and I'll be constantly looking back at their solution because this is new to me as well. All right, but before I do, let me just understand what this thing is doing. It's one-dimensional. X is now not starting at 0. It goes everywhere. It goes infinitely far in both ends, but time only moves forwards. And then phi is some function that has a value at every x and at every time. And it must be a function of both x and t because I can differentiate it with respect to x. That's what the phi xx means. It's short for the second derivative with respect to x. And phi tt is the second derivative with respect to time. Okay. And then this is telling me that when time is 0, the phi is some function. So there is some function that tells me what the value of phi is at every spot here. And this is saying that the derivative of phi with respect to t is equal to 0 when time is 0. Okay, so that's telling me it's stationary at the beginning of time. And this phi could be a displacement, in which case that's saying that the speed at which phi is changing at every particular x, that's what phi sub t means. When it's beginning, it's not changing at all at that exact moment, and then it might start to move after that. Okay, that's what the equation's telling me. And now I'm going to see what happens when I attempt to do Fourier transforms on it. And that's going to require me to know what Fourier transforms do to derivatives, which I wrote down right at the beginning, this. Differentiating on this side is the same as multiplying by IW on this side. Okay, so Fourier transforms turn position into W. So I'm going to assume, yep. Where'd the chat go? Is this a D'Lambert's problem? I don't know. Probably. I could look that up. Okay. So D'Lambert's problem is usually done with separation of variables or Laplace transforms, is it? And that it says to use Fourier transforms to do it in this problem. Yeah. Okay. Oh, okay. So the x's go from minus infinity to plus, so, you know, do with Fourier because you were told to. That were the instructions, sorry. Didn't say that. So the x's go from minus infinity to infinity, which seems reasonable. And if Fourier transforms are designed to turn x's into things, so I'm going to assume I'm going to do the Fourier transform on the x's and turn them into w's, and then see what happens then. Okay. All right. So all my x's are going to turn into w's. So I'm going to go that the Fourier transform of phi is going to be phi hat. And this would be a function of, this would be a function of x and t. And this would also be a function of t, because the Fourier transform is done on the x's, and it would change the x's into w's. Okay. And so in the same way as the Laplace transform, which turned t's into s's, but the x's stayed where they were, anything involving t will stay exactly as it is. So phi of xt is becoming phi hat of wt. Phi tt would still be phi hat. The phi would become a phi hat, but the t's would stay as they are. Phi xx, that means I differentiate with respect to x, and differentiating with respect to x is the same as multiplying by IW. So I differentiated it once, and then I differentiated it another time, like that. So this one is double derivative. Crap, other way around. This one was a double derivative. And doing derivatives with respect to x here is the same as multiplying by IW. So this would be multiplying by IW twice because I did the derivative twice. So I get this. And so that would be I times I, which is -1, and W squared. Okay. Right. So I've dealt with this. I've dealt with this. This has got an x. I guess I could turn that into a Laplace Fourier transform to 5x0. When I do the Fourier transform, would be phi hat of w0, because the t stayed as a t, and the f of x, when I did the Fourier transform, would become an f hat of x. And then the phi sub t would still be a phi hat sub t, and the x0 would become an w0. And then 0 just becomes 0. So every piece of this, I have now figured out what it looks like as a Fourier transform. I'm just going to copy that down again, just to make sure I've got this right. And so I get that the phi tt became a phi hat tt on my list. The c squared is just a number, so that's going to stay the way it is. The phi xx became -w squared phi hat. This became phi hat of w0 is f hat of w. Sorry, that should be w there. W, yeah. And phi t became a phi hat t, and that's still 0. So we've turned this into this by doing the Fourier transform. How do people feel about what happened there? Okay, I'm going to look at this. This is now saying that the second derivative of phi hat with respect to t is this minus c squared w squared phi hat. Which is a second order DE with constant coefficients. It's, if I'm going to write it sloppily, phi hat double dashed plus c squared w squared phi hat is 0. The second order constant coefficient DE. And so its characteristic equation, because it's a second order and it's constant coefficients, that would be lambda squared. Probably could have left it like this if I want to. I don't need to make it equal to 0. It's even homogeneous. Lambda squared is minus c squared w squared. So lambda is, that will become an I, like that. Well, yeah. So important question, does that mean w is constant? W is constant when I'm thinking about this derivative. So now I'm going to go think about d on dt's. And when I think about those derivatives, now I think w is constant. Yeah. I had a question earlier that I missed. Why is the phi hat t w0 equal to 0? That was because I transformed this. The phi became a phi hat. Differentiating with respect to t doesn't get affected because the Fourier transform only affects the x. The x becomes a w. The t is 0 and the Fourier doesn't affect the t, so it's still a 0. And the Fourier transform of the number 0 is still 0. So that's what that happened there. So now we're at this stage. This is a second order DE that's constant coefficients. It's got a characteristic equation. We've got this. And when you've got those things, the two solutions will be cos of this t, because it's a d on dt, it's the things are in terms of t, and a sine of cwi t. I'm really hoping I'm doing this correctly. Oh no, don't do that at all. That's okay, ignore that. Complex numbers are allowed now. Okay. Right. Where here complex numbers are allowed. Back when we're using, because we've done a Fourier transform, we're allowed to have complex numbers flying wherever we want. And when we used to do constant coefficient DEs, we used to see an imaginary one and we'd interpret that as a cos and a sine. But now because complex numbers are allowed, we're going to interpret it as an e to the power of. And so I'm going to get e to the power of CWIT and e to the power of CWIT minus. So these two numbers plus CWI and minus CWI become e to the power of, and it's a t because this was a dt that we were thinking about. Okay. All right. And so my solution is now that that phi hat is equal to some constant times this plus some constants times this. But because we were doing this in thinking of d on dt, which meant that w is a constant, any constant that we introduce is technically allowed to be a function of w. Right. So this is where I'm at. Okay. So what would I do now? Normally what I do is I try and use the conditions I've got to figure out what these constants were. So I'm going to do that as well. Phi hat of w0 is aw e to the 0 plus bw e to the 0, which is a of w plus b of w. And phi hat t of wt would be the derivative of this with respect to t. Oh, just a second. This is supposed to be f hat of w, because that's what the condition here said. I do the derivative with respect to t. The aw doesn't have a t in it, so it will still be there. We'll have an e to the cwi t, and that will give you a cwi here. And I'll get minus cwi this time when I do that same process. And now when I do phi hat t of w0, the e to the power ofs will become e to the 0, which is 1. And I get this, and the initial condition said that this is supposed to be 0. So if I divide everything by cwi, I'm going to get aw is the same as bw. So I reckon I can sub this back into there. I'll get that 2 lots of AW is f hat of W. And so AW is a half of f hat of W, and BW is the same as AW, right? And so now that means that my phi hat is now this. Oh, it's so cool. Fun. I'm going to pull out the half and the f hat W. Oh, okay. The thing I said so cool to in the moment is that I don't know if this is important, and I'm just going to write it down and then possibly not use it. This is cosh of CWIT, because cosh is e to the thing plus e to the minus thing divided by 2. Yeah. Not that I know what that means, it's just interesting. All right. Okay, so just a second. I'm going to have to Fourier transform the f hat to the phi hat. The actual phi is going to be the Fourier inverse transform of phi hat, which means I'm going to have to do one of those integrals. Oh, and maybe I shouldn't have done this cosh thing. It just looked so cool to me, that's all. Yep. Oh no. There's probably some mega convolution thing, isn't there? All right, this is where I'm going to look at the solutions and show you what they look like as well. But something happened in the chat just then. Yeah, it's probably better to use the Euler formula instead of Koch. It just was cool. That's all. That's why I crossed it out. Okay. This is where I'm up to here. Got the same as them here. Inverse Fourier transform. So the f hat here has become a convolution here. Ah, what? There's some moves here that I'm not 100% sure of what's going on at the moment. So some things that I need to figure out about what's going on the page here are these. So they've said that we need to do the inverse Fourier transform of half of f hat, and they've gone all the way back to here. So we've done the Fourier transform of each piece separately, which is okay. Thank you. And then we're going to get a half. And apparently there's a theorem for convolutions, which I should look up as well. So if I've got two things multiplied together, then the Fourier, this one just here, two things multiplied together, then the Fourier transform of the convolution will be the product of the things. So that means if I've got a product of with a root 2 pi, the product of the things when I untransform it should be the convolution. So this should be 1 on root 2 pi times the convolution. Is that what they did in their solution? Why are there no 1 on 2 root 2 pi's in here? This is confusing me. Like if this is the truth, this one here, then shouldn't, when you have two things multiplied together, it be 1 on root 2 pi of the convolution? Or has my chat not appearing? Cancelled with the delta function. Oh, just a second. Okay, thank you. I see what's going on. I'm going to do it one step at a time if that's okay. So the inverse transform, thank you so much. The inverse transform of f hat is straight f, x. And apparently the inverse transform of e to the c thing is root 2 pi of delta thing. All right. And so then we've got a half, we've got a 1 on root 2 pi of f of w x. convoluted with root 2 pi delta cx plus ct. Okay. And then these cancel. So that's where that comes from. And it seems that when you convolute a function with the Dirac delta function, you just sub this in here, which is cool. I didn't know that. So there's a lot going on in that example that I've literally never seen before. And these are what the rules seem to be, that the Fourier transform of the delta of x plus a is e to the a w. No, iw, apparently. I don't know how we're meant to know that. Apparently there was an example in the lectures. It wasn't in the notes. It must have been in one of the videos. So I think a useful thing to do would be to go through the videos and find all the answers we've got. But I'm just going to do it. So some facts. 1 on root 2 pi. Oh no, there'll be a root 2 pi here as well. 1 on root 2 pi times the integral from minus infinity to infinity of the Dirac delta function of x plus a e to the minus iwx dx would be, okay, so the Dirac delta function has the property that when you integrate it on any interval that involves 0, the answer will be 1. Basically, example 104, it was done in a lecture. Yeah. But it requires us to know a whole lot of stuff. Subject to your comment about expecting a delta function to come up because of localized source. Unfortunately, that means nothing to me, and it might mean something to other people, but there's information about what these words like localized source mean that doesn't seem to be in the course, at least for me, who hasn't seen any of the lectures. Yeah, so as you know, I'm not part of the people who run the course, so I don't know all the details of everything. Okay, so I'm not going to do that. I'm sorry. That's something that if it was in the lectures, you can go and watch your lecturer doing it. But this is apparently the truth. And some other facts are that when you convolute a function with the delta Dirac function, then what you get is this. That's a second fact that we're apparently supposed to know in order to make sense of this example. So I have a feeling that there's some magical properties that the Dirac delta function has, so that it is designed specially to do some of these things. So if you were really familiar with the Dirac delta function, then using the Fourier transform to solve these things would make this easier, because you go, oh, well, I know how to convolute the Dirac delta function. It does, you know, this is what happens when you do that. Yeah. So I think these are some things to add to our list of useful pieces of information somewhere that you can look up. Okay. It really is time for me to probably stop very soon. I'm feeling marginally better about how the Fourier transform works on these partial differential equations. It seems that the hint is that if there's an x involved, then running the Fourier transform might be helpful, but again, you can do this one without that. And that Dirac delta functions appearing because of exponentials is why that's useful, because the exponentials appear because of solving the differential equation using constant coefficients, and then they turn into Dirac delta functions, which cause us to sub things into other functions. Yeah. Okay. Going to look for one more thing. Look at this. I Googled table of Fourier transforms, and this is the thing that we would really like to have known. The Fourier transform of the Dirac delta function. These are t's instead of x's. All right. Well, we would have to adjust for that. This x would become a 1. Yeah. So there are in fact answers. Wow. No wonder they didn't give it to you, because this looks insane. Oh, here you go. There's Dirac delta functions here that are causing causes and sines to appear. Okay. Good-o. So here we go. I think this is a different kind of Fourier transform than the one I'm expecting. This one doesn't have the 1 on root 2 pi. This has a 1 on 2 pi, not a 1 on root 2 pi. So this one's a bit different to what we've been doing. We can probably find one that has the correct things. But all I was saying is that it would be nice for us to make a list of our own, possibly your lecturers to make a list of the ones that have appeared during the working. We have 2 so far. Yeah. We have this one. Sorry, just a second. We have this one. And we have this one. These are the 2 actual Fourier transforms that have occurred in examples in the lectures that we've noticed. There might be others. Yeah. All right. I'm actually going to stop. If you have any other questions, then feel free to drop into the Maths Learning Centre and chat. I will be there most of the rest of today in the Zoom. And I really wish you well with your study. And yeah, this bit is confusing, and I hope I've made it a little less confusing for you, so that you have a chance of writing something down that's useful when you're in your exam. Thanks for bearing with me. The videos will probably not be ready until tomorrow morning, and I'll send you an email when they are. But the old videos are there. Yeah. Good luck, everyone.